Yeah. Yeah, I used to say that all the time, and then I was like, I was trying to make it like a YouTube video, right, where you always have the same intro, but then people started making fun of me for it, so I stopped. But yeah, this is so let's get started. We are September 25th. We're going to finish up memory management today, more than likely. I guess I'll address the fiasco with the tutorials. So Gradescope has no mechanism for me to deduct marks for late tutorials, so I had to sort of invent my own. So I wrote it into the Python code. So it basically grabs the current date and time from the operating system, which apparently is way off because I gave it 24 hours leeway, and it still was marking people late who were before the deadline. So that's out. So I changed the marking scripts and I remarked all your tutorial twos. Some of you, most of you, probably it went up if you were late, or it stayed the same. A couple of you may have dropped. If that happened, contact me. Usually what that means is that you got lucky when you submitted it, which, I mean, that can happen. Because I pick some random numbers sometimes, and the random numbers are such that it's looking for a number over here, and it finds it over here, and it's happy. So that can happen. It usually means there's a, but if your mark went down, then maybe there's a small problem with your code. Anyway, we'll figure it out. And I'd remarked tutorial 1 just maybe 20 minutes ago. So same thing for that, right? Because it affected less people in tutorial 1, but there were a few people who were marked late who weren't supposed to. So what that means is, I don't know. I do have a way of marking your tutorials late. I have to download them all. So right now, if I want to transfer the grades from Gradescope to Brightspace, I click a button. That's great. I like that. If I want to mark yours late, I have a script that'll do it, but I have to download all your grades from Gradescope. I have to download a Excel sheet from Brightspace. I have to upload those grades to the Excel sheet by running a script, and then I have to upload them to Brightspace. And that's a real pain for 10% of 1%, right? So it's like 0.1% of your final grade. So as it stands, your tutorials officially, if they're late, they might lose 10%, but I'm really feeling like this amount of work is not worth it, and I might find another solution, but until I do, you know, I'll post. Nobody will be marked late up till tutorial 2, 3, and beyond. If I come up with a solution, we'll see what happens. But yeah, so that's where we stand with the tutorials. But again, if your mark went down on tutorial 1 or 2, please let me know. We'll look into it. Assignment 1 is, of course, due on Saturday. Tutorial 3, or sorry, Sunday. Tutorial 3 is due on Saturday. Tutorial 3 is just a tester for adding events to your planner date, basically. And then the assignment, the scripts that are run there, put those 2 classes together with your planner, and or those 3 classes, I guess: planner, date, date and event, and then make sure that they all work together well. But yeah, so that's yeah, any questions on any of that? Okay. So last class we were talking about memory management, or we started talking about memory management. I don't think we got very far. And again, some of this is review because I've been talking about the stack and the heap right from the very beginning. I guess because they're important concepts, and I really wanted to nail those concepts home. If you have a good model of how your computer works and how C++ works, then you will be more likely to, or more capable of writing good code. Maybe I've harped on too much. I don't know. We'll see. But so yeah, stack and heap. So we had talked about the 4 areas of memory that are allocated when your program starts up. So we have the function call stack and the heap. There's also the data segment and the code segment. I think I covered the data segment and the code segment, right? But basically, code segment has the program instructions, and the data segment contains things like global variables, static variables, and string literals. And then we have the function call stack. Keeps track of the functions called and the order in which they were called, and stores all of the local variables, stores function parameters, and a little bit of other metadata for these functions. The heap is where we store all dynamically allocated memory. That's sort of your little memory place. And basically anything we allocate with the new keyword goes on the heap. Anything we don't use new with does not, unless it's part of something else that's on the heap, but that's sort of different. Okay, so function call stack. We've talked about a stack is like a plate of dishes, right? So my function call stack operates the same. When I put a new function on, it always goes on the top. And when I return from that function, I pop that one off and I go to the next one down. And it's sort of like a stack of plates. What I never do is if I pop this guy off, I never jump down to the bottom or something like that. I always read through each function in turn on that call stack until I return from it. Adding something to a stack is known as pushing the item. Removing something from a stack is known as popping the item, right? So these are stacks in general, but specifically we care about the function call stack. So yeah, that just gives you, anyway, we've covered that ad nauseum. The heap also we've covered ad nauseum. Yeah. All right, so we'll briefly go over statically allocated memory. This is basically review. When I statically allocate a variable, it's reserved wherever the context of the variable is. That might be inside another class or a struct or something, or inside of a function call, or inside of an if statement, any of those. This memory is deleted for us. So once we leave the context or the context is destroyed, then statically allocated memory is deleted, whether it's an object or a primitive or what have you. Dynamically allocated memory, we explicitly create it using the new keyword, and we have to delete it explicitly. So we manage the life cycle of these things. So that is one advantage of using the heap. The other is that the heap is a little more flexible in terms of memory. If I have huge data structures, I don't want those on the stack. That's a big mistake. You're going to get a stack overflow, or at the very least, you'll have a lot less room to work with. The heap is not just a place that's a pain to use. It's actually very useful in the sense that I can allocate huge data structures there, and they don't interfere with the running of my program. But when I put objects on the heap, what gets returned is a memory address. And specifically, I'm going to use the words memory address and pointer sort of interchangeably. They're the same thing. Right? A pointer is a memory address. It points to a memory address. And when I use the address of operator, that returns a pointer. Okay, so these are interchangeable terms. But when I use the new call, when I make a new date or what have you, a date is allocated on the heap and a pointer to that is returned. So that's one of the main reasons we use pointers is, well, we have to for dynamically allocated memory. The other is, well, similar to the reasons why we use references, is that they're actually small for a computer. They have a fixed size of 8 bytes, which means one trip down the memory bus, or the address bus. Right, so one cycle of my CPU, I can grab some memory from any address by just writing 64 bits. It is often smaller than the data it points to. That's not the case so much with primitives, but it is the case with objects often. And that makes it easier to pass the pointer by value. Right, so that means function calls are going to be faster because I'm not copying huge objects. I'm simply copying a small pointer. They're also an easy way to avoid copying data. When I move around pointers, they're sort of very light and convenient, and they avoid copying the objects that they point to. I can make lots of copies of a pointer, that's no problem. But yeah, they're all pointing to the same object, and I can use that in various places. Okay, so all pointers have a name. They have a data type. Technically, their data type is pointer, but pointer to something, right? So int, date, what have you. They have a value, and this value is a memory address, right? And then if I follow that memory address, then that returns whatever I'm pointing to. And that must, so the compiler keeps track of the type. So when I return when I follow that memory address must contain an int, a date, whatever this is a pointer to. Or at least, at the very least, the compiler is going to pretend it's that. Even if it's not, maybe it's a piece of garbage memory, it's still going to treat it like whatever it thinks it is. Also, these pointers have their own location in memory. So they have their own memory addresses, and I can point to those pointers, as we will see. Okay, so let's just in detail now go over sort of what happens with these pointers. For some of you, this might be review. You've probably seen it in 2401, but so I have my character C, and let's say that, so these are hexadecimal numbers, right? There's two of them. A typical memory address would be a lot more than that, but let's pretend. So these are the memory addresses of these variables. So the first one is a character C, and let's say I declare it by saying char C equals H. So the name is C, the type is char, the value is whatever the ASCII or Unicode or whatever it is for the letter H, and its location is A8. Next, I can declare an integer, I equals 42. So that is a variable named I. It's of type int. Its value that it's stored at is 42, and the location that that value is stored at is A9. And then finally, I can declare a character pointer. Presently, I will have it pointing to nothing. We will pretend that it's null. It's not necessarily the case. But, well, actually, let's say star C pointer equals null. Okay, so then this is, the name is C pointer. The type is char star, so a character pointer. The value is currently null, and its location is A8. Okay, so then let's say I did something like C pointer. No, I don't want to dereference that yet. C pointer equals, and I want to point this at my character C, but C pointer points to a memory address. So I want to grab the address of C so that it's pointing to the same thing. So I have ampersand C. And what that does is it says, well, assign the value of the address of C, or the location. The location is A8, and assign that to character pointer. So now that looks like this. Now, if I take my character pointer and do something like cout dereference char pointer. So what happens? Well, first, the program does the dereferencing, which says, well, here is the value that's stored in C pointer, but I want you to follow that memory address and return whatever value you find there. So we we jump to A8, which is here, and we return the value that's there. That's this H. So now this H gets output. Yeah, I'm running out of space, but the output is H. If I tried to say cout character pointer directly, well, because it's a character pointer, something really weird would happen. But typically what we expect if we send up pointer to some sort of output is we'll get the hexadecimal address, right? So this would output something like this. OX means hexadecimal, and then A8 is kind of small in this case. It would be a whole bunch, forget exactly how many, but it would be a whole bunch of numbers and letters, 0 through 9 and A through F, is it? A, B, C, D. Yeah, perfect. Okay. That's not what happens with character pointers, but we'll get to that in a second. But any questions? Okay. So let's see that in action. Okay, so this is the example that we were looking at before. Let's make this a little bigger. And from B, CB06. Okay. Okay, so the first thing we do, we make a character C, we assign it H, we make an int I, we assign it 42. We make an int pointer and a char pointer, and then we're just going to look at the size of these things, right? So we have this size of function, which I believe is from C. So I check the size of this variable, right? So how many bits do I need to store this letter H versus the size of the pointer to this variable. And I do the same thing with the int. So we'll start with that. Oops. Okay, so the size of my character is 1 byte, 8 bits. The size of the pointer is 8 bytes, so 64 bits. The size of my integer is 4 bytes. The pointer is 8 bytes. So for primitives, often that's the case. I don't really care. Passing around a pointer or making a copy of a primitive, they're both sort of cheap operations in terms of how many CPU cycles it takes to copy them. Okay, so, but the real savings come when I do something like this. So I have my date class. How big is date? Well, it's essentially big enough, at least for 3 integers, and then maybe some metadata. How big is my calendar? Well, I have this max array is defined for 366, and I statically allocate an array of date pointers of size 366. So this is going to be significantly bigger. But yeah, so my date is 8 bytes. The date pointer is, or sorry, the date is 12 bytes. The date pointer is 8 bytes. My calendar is 2,000, almost 3,000 bytes, and the calendar pointer is still 8 bytes. So you can see by passing around pointers or references, we save a lot in terms of copying these things everywhere. But questions? Okay. What's the other? Yeah. I was going to show you. So we can print out a pointer, let's say. So I pointer, because that one will actually work. And this will return, and then yeah, we'll come back to character pointer in a minute. So if I print out I pointer directly, then I get this weird number, right, which is a memory address. If I dereference it instead, then I actually get my number 42, right? So pointers look like this. If I try to do the same thing to my character pointer, then I get H star, which is yeah, a little weird. So So yeah, my I pointer gives an address. My character pointer doesn't give an address for some reason. It gives this H star thing. So what, anybody know what's happening there? I don't know, just any old guess. I don't, this is not super important, but in case you ever run into this, you'll know that, if you try to send a character pointer to the standard out, it's not really going to work the way you think. And the reason is because this is basically built on top of C. And in C, when we print stuff, we basically start with a pointer, right? So we have a pointer to an array of characters, and then C will read through until it gets to an end of string marker, whatever that happens to be, maybe a 0 or something, and then it stops. So that's what it does here. If I give it a character pointer, it tries to treat it like a string instead of like a pointer. So anyway, that's it's funny. I remember one of the first times I taught this class, I did this and I got the H and I was like, I don't know why that happened. So I had to look it up after, but yeah, it's always fun. C++ always contains a bunch of surprises. Of course, I can do things like this. My I pointer points to this variable I, so they both have the same value. And if I reassign that value, really, did I forget this? Save. Yeah, okay. So if I reassign, it starts out both of these. I gives me a value of 42, and a dereferenced I pointer gives me the value of 42. I can assign that variable a new value using my pointer or using the variable, and they both reflect the new value. And one last thing, this is, you don't have to know this. I just thought it was interesting. So my I pointer, of course, as mentioned, it has an address. And technically that address is a double pointer, right? Because it's an address and a pointer are the same thing. So it points to an address that points to an integer. So I can declare a double pointer and assign it the address of my single pointer. And then I can actually declare a triple pointer and point it to the address of my double pointer. And I can declare a quadruple pointer and point it to the address of my triple pointer. And how deep do you think we could go? And then I can dereference my quadruple pointer 4 times. And I get back my original 99. So yeah, I just thought that was kind of interesting. And the spec for C++ technically can go 12 deep this way for whatever reason. I don't know. I know double pointers are used. Probably there's use cases for triple. After that, I don't know. Yeah, just an interesting aside. Any questions? Okay. Okay, so yeah, when we declare, of course, a pointer, we include the type of data being pointed to, a pointer symbol to indicate that it is a pointer, and the variable name. Yeah, of course, pointers can receive, I do not just have to assign a pointer something that came off the heap. I can take some statically allocated variable, grab the address and put that into a pointer as well. So yeah, they'll point, they don't care where this memory address is as long as it contains the correct type. So this symbol is also, so it's a pointer, but it's also called the dereferencing symbol because if I dereference a pointer, it's going to return the value stored at the memory address, right? If it's an integer pointer, it returns an integer. If it's a date pointer, it returns a date, etc. These pointers can also point to null, right? So, and really I should if I'm not going to use that pointer, if it's in some sense dangling, right? So maybe I have a pointer, I deleted whatever was at the end of it, and now it's pointing to garbage. I should set that to null pointer. So why? Because, well, I could do a null pointer check, first of all, to make sure that my pointer is pointing to something useful. And if I just delete it and I don't change it to null pointer, then I can't do a null pointer check. There's no way to verify that that location has good data in it. The other thing is maybe I try to call print on a dangling pointer and it's pointing to some weird memory location, and maybe sometimes it works and sometimes you get a seg fault and sometimes it just loops endlessly. There's all kinds of stuff that can happen. But if it's pointing at null pointer, I get a null pointer exception, which is nice because it crashes. And I know exactly where it crashed, right? So that's a couple advantages of setting dangling pointers to null pointer. If I have a pointer to something and I delete and then I exit that function right away, and then that pointer is being erased, then you don't have to set it to null. That's really if I have a pointer that's hanging around that's not pointing to anything. So yeah, good programming practice is to check for null pointers. These symbols that we're using for our pointers have different roles, right? So when I'm declaring variables, this indicates a pointer, this indicates a reference. Anywhere else, this is a dereference operator. This is the address of. This is, of course, also multiplication. And I think it has some bit operation that I can't remember. So context matters a lot. There's a lot of C++'s. Yeah, you can infer a lot from context. Sometimes you got to help it along, though. But yeah, so pay attention to the context. Parameter passing. So we talked about pass by value and pass by reference. And this is sort of a repeat of what we looked at before. So I don't think we're going to do this example unless somebody wants clarification. But we did this before, right? So when we were learning about reference, we did get input and then double the number using a return parameter. And I did show you how to do the same thing with pointers. If anybody wants to review it, we can. Anybody? Yeah. Did you put a... Yeah. Yeah, just to clarify, so this is called passing by, yeah, it is confusing. This is called passing by reference in general. And then there's passing by reference using references, which is specifically this case. So yeah, that's confusing, I guess, because we're using reference an awful lot. This is passing by reference using pointers. Right, so when I say pass by reference, it could mean either of these cases. It just means I'm passing the address and not the value, right? I'm making a copy of the address and I'm passing that into the function instead of copying the value of the int. Both references and pointers do that, right? They copy the address. The difference is passing by reference, I can treat this as I would treat any other int variable, right? So the difference is the syntax. There's other differences too, but they're less important. The main one is I cannot reassign this to point to something else. The pointer, I could reassign this. I could say res equals new int if I wanted to. But, you know, that's sort of an odd case. For the most part, these are functionally the same. They're just syntactically different. But yeah, other questions or clarifications? Okay. So yeah, memory allocation, just as a review, static memory allocation, I declare a variable, memory is reserved wherever it is declared. It is reserved in the context. So if I declare it in a function, the memory is reserved on the function call stack. If I declare it inside another class, the memory is reserved with that class wherever it happens to be. If I declare it in the middle of an if statement, then the memory it's on the stack, but it's inside that context. And when we exit the if statement block, that memory gets reclaimed. Same with a for loop. Dynamic memory location. So this is sort of a lot of different applications or a lot of different locations it could be. Dynamic memory location is one place. It's going to be on the heap, and there's only one way to allocate it, and that is using the new keyword. So anytime you see new, that is dynamic, and it will be on the heap until we delete it by calling delete. Yeah, so a couple things to keep in mind. When I use new, it calls the object constructor. So new actually behind the scenes does a call to malloc, but then it also calls the constructor and runs that and initializes all your variables for you. If you just use malloc itself, I believe the compiler will let you, and you can initialize things on your own, but that's sort of defeating the purpose. When I call delete, that reclaims, it does a call to free, but before it does that, it runs the destructor. So it's going to clean up all your memory variables, and then it's going to reclaim that memory. And that's sort of important, that we clean up the resources first, and then we release our own memory, because that allows us to sort of have these destructors set up like dominoes, right? So I delete this guy deletes a whole bunch of other objects, and those objects go on and delete other objects. And at the end, all my memory is reclaimed. Let's see, I don't know if I want to run. Yeah, I think we've seen enough heap examples. So yeah, we'll skip that one too. It's basically just using new and statically allocating variables. We've seen that ad nauseum. So let's talk about memory leaks. So this is going to be more important on assignment 2. We want to avoid them. So yeah, C++ and C do not provide garbage collection. So that means you can have memory leaks. Technically, you can have memory leaks in Java as well. I've done it. It's more difficult, but it's not impossible. But a memory leak is a block of dynamically allocated memory, so using new, but I have no pointers left to it. So I don't know, I have no address, variable holding an address to it. And once that happens, I can never again use that piece of memory. As long as my program is running, it has a claim to it, but it can never be released because I don't have a pointer. So I can't call delete on it. Once the application exits, all the memory is reclaimed. So you can always do a reboot when you have memory leaks, but yeah, you cannot reclaim it while it's running. So what causes it? A pointer gets clobbered, in other words, overwritten. I declare a pointer, I allocate a new memory location, and then that pointer goes out of scope. That's another possibility. So why are these a problem? Well, we lose access to the data, which I guess that's bad. But also, you know, industrial grade software runs for months or years. And of course, if it runs that long, the code's going to repeat. And if the code with the memory leak repeats, then the memory leak gets repeated, and then your heap fills up and fills up and fills up, and eventually you have to reboot. So yeah, just as a story, because I like this story. So this is the file explorer for Windows 11. And back when Windows 11 came out, I was sort of an early adopter. I always am. I don't know. I like it when stuff breaks and weird things happen. But if you look at Control-Alt-Delete, Task Manager, and we look at, let's see, where is it? Windows Explorer is here, and it uses about 60 megabytes. And if I close it, it uses about 66 megabytes. So it doesn't actually close, it keeps running in the background. And if I boot it up again, you can see that it goes up to, now we're at 98. So it does a bunch of indexing when it boots up. So it grabs a bunch of memory, but then it'll eventually settle back down to somewhere in the low 80s. Okay, so this, and I can do that as many times as I want, and the amount of RAM it's using stays the same. So when Windows 11 first came out, it had a huge memory leak in this. Like it was well documented, and I saw it for myself. I actually presented it to the class at the time, but so you'd boot it up, you'd get about 60 megabytes. You would close it, it would stay at 60 megabytes. You would open it again, it would go to 120. You close it, it stays at 120. You open it again, it goes to 180. So every time you closed and reopened it, it just grabbed more and more memory. So yeah, it just goes to show you even professional programmers, which you guys will be in a few years, they can make these kind of mistakes, right? Memory management is difficult. And at the OS level, you're dealing with things like C and C++. So yeah, they eventually fixed it though, but I don't know. It was pretty hilarious how obvious it was, and you wonder how they could have missed it, but I guess these things happen. So yeah, let's make some memory leaks. So the first thing to note, so here I've made a pointer, I've assigned it null pointer, and then I'm going to, what is this? Yeah, T3v2, permission denied. Okay. Not remove T3v2. So that is a problem some of you have had, or some people that I've talked to have had this same problem, right? It couldn't run this executable. And the reason why is because it was compiled on my machine, and I'm running this on OpenStack. So I had uploaded it, and you'll get the same thing when you try to run things on Gradescope. Because I forgot to clean it, when I ran make clean earlier, it did not remove it, and I don't have permission to run this in that system. Now, it's really easy to add permission, right? It's a chmod. But I prefer to run the clean step to make sure that you've cleaned everything correctly. So yeah, at this point, okay, so I just ran a piece of code that did nothing, or looked like it did nothing. I made a null pointer, and then I deleted it. Okay, so that's the nice thing about null pointers, is you can delete them, and if you accidentally delete something that's null, it's not affected. Okay, so that's a little something the compiler does for you. But yeah, now that we've done that, let's make a memory leak. Okay, so what did I do here? Right, so yeah. What's that? Yeah. Yeah, exactly. I overwrote it. We call it clobbering it, or depending on where you work, they probably have a different nickname for it. But yeah, I clobbered this. So this returned a memory address that I stored in this pointer, and then I assigned it a different value without saving this old value or deleting it. So even though I delete P1 here, this is going to give me a memory leak. Right, so I lost 4 bytes, which is the size of an int. Yeah, just by clobbering it. Okay. The other thing I can do, let's say I don't do any of that. I call this function called memory leak. This function called memory leak, I declare a pointer and I assign it a new int. I write it out and then I return. What I didn't do is delete this memory, and I did not return this pointer. So I lost, this pointer gets deleted when this stack frame gets popped off. I lose the reference to this dynamic memory. And again, I have a piece of memory on the heap and I have no way to delete it. So I definitely lost 4 bytes in that case. All right, questions so far? Okay, what about this one? Is memory leak? So just for fun, what do I want to do? Yeah, I want this. Okay, so I assign P1 this. I'm passing P1 into this function, is memory leak. Is memory leak. I take this pointer and I assign it a new, maybe I should make it just to be clear that this is a different int. I make this new int. I output it and then I delete it. Is this a memory leak? And I guess the question is, did I clobber that pointer that I passed in? Did I clobber P1? This is a tough one. It's tricky. Did I? I clobbered it in the function itself. I definitely did that, right? So, but does that change the address of P1? It's meant to be tricky. Did I not save it? Not saved. Okay. Okay, so I-55 returning from memory leak, this should say is memory leak. But oh yeah, I definitely lost 4 bytes. And why did I lose 4 bytes? Because let's properly manage it and then see if I stopped on anything. Okay, so in this case, all heap blocks were freed. So you were right, I did have a memory leak, but because I forgot to delete P1. But yeah, I didn't stomp on this. So the value of P1 never changes, right? I pass it in, I passed in a pointer by value. It makes a copy of that address, and that copy of the address goes into this variable here. And then I stomp on it, but that's okay because I still have this original reference. Okay, so that one's a little bit tricky. Kind of important though. Yeah, questions? Okay. All right, so those are all the ways that we can have memory leaks that you should try to avoid. But those are small cases. We're going to have big, data structures full of things. So we want to have a bigger strategy, right? So, I mean, there's a couple rules of thumb. And for one, if you see a new, you should always have a delete somewhere. And a good rule of thumb is wherever I create an object, I should destroy it. So if I create it in a function, if I call new in a function, I should call delete. If I call new inside of a class, I should call delete in that class somewhere, possibly the destructor or in the remove function. And so what we're going to do as a general strategy is we want to take all our dynamic memory and delete it in the constructor of some other object. Okay, and if we always do that, or in the remove function or somewhere else, but at the end, when we delete everything, all dynamic memory should be destroyed in some destructor, and exactly one destructor, because if you do it twice, you're going to get an error. So we're going to tie all our dynamic memory, the lifespan, to some other object, which would be tied to some other object, which eventually we'll either have one object or we'll have a bunch of statically allocated objects that are deleted for us. So that's going to be our strategy for memory management. There's exceptions to this strategy that work quite well, such as the factory design pattern, but we'll see those later. Okay. We haven't talked a lot about, so we're going to get to collection classes. A lot of you are going to be tempted to delete your dynamic memory in your collection class. Go for it. I encourage you to experiment with memory management and see what works and what doesn't. And you will not lose marks if you don't have memory leaks. That's the bottom line. Okay, so there's reasons why I would not delete my objects in my collection classes. Sometimes it's really convenient to do that. It depends on how you're using them, but I'll leave that up to you guys. It's possible if I could have multiple game lists in my game application. I can have my favorite games, my high score games, multiplayer games. I've stored in various locations, but I don't actually have copies. I just have different pointers to the same games. And then if I remove one of those lists and delete all the games in it, then I can wreck all my other lists, right? So that's one reason why not to, but okay. So yeah. So using this resource acquisition is initialization. We're going to have this hierarchy of deletion responsibility, or in other words, a domino effect. I delete my top level object, it deletes a bunch of other ones that delete a bunch of other ones, and so on. Okay. All right. So let's take a look at which time we got. So just sort of a simple example of what we just talked about, this high level. So I have a calendar class here, and I have a date that I've modified. So this is a little bit like your assignment. I took the date class and I added an event, right? So your assignment's this, but a little more complicated because you can have multiple events on any given day, and this only has one. Sort of the same idea though. I have a date and I have an event associated with that date, and I can check to see if this is equal to that event, and so on. So when I make my calendar and add a date, I'm adding, so this is a scheduler, a very simple scheduler compared to assignment 1, but sort of the same idea. I'm going to add a bunch of dates. They'll be stored in sorted order by the date, and then I'll have a bunch of events that are planned out for me. And then we'll have, so we're just going to quickly implement this and then manage the memory for it. So my add date, I don't explicitly add a date pointer. What I do is I check to see if I have room in my array, and if I do, I'm going to, yes. All right, so Copilot's going to do the writing for me. Simply, we've seen this before. We've done it in detail, this add function in order. So we have to, of course, figure out where it goes and insert it and make room. But we'll see if Copilot, you're not doing it correctly. So yeah, let's say. All right, we want it the other way, right? So we want this. So yeah, this is, it's nice to see this doing some weird stuff. And I know like not everybody here has Copilot, but if you use a large language model like ChatGPT to try and do these things, it's going to do weird stuff. This has to be dereferenced. Like invent a function and assume for whatever reason that you have it, right? It's a large language model. It does predictive text, basically. It's autocomplete, but fancier, right? With much deeper learning. But what it doesn't do is reason. It can't see that I don't have this function. It can guess it reads the rest of my code and makes guesses, but it does some stupid things too. So just beware if you use it. Again, I'm not going to explicitly say that you shouldn't, because these are the tools that you'll be using moving forward in your career, but just be cautious. Make sure you learn how to code. So let's do. Okay, so this is going to advance to the right location, and then I'm going to make room for the date. And then I will assign the date to the proper index. I will increment number of dates. and return true. Okay, and I think that'll work. Maybe there'll be some mistake, but that's not really the exercise here. Any questions on that? Okay, so this is an add function we saw before. I wanted to try it with Copilot and see if it worked. We also need a print in order to be able to test it. So yeah, that's simple enough. We simply loop from 0 up to num dates. We know each of those has a valid date in it, so we call print on. Okay, and then in our main function, we're going to get rid of all those. We're going to make a calendar, and then we're going to add some dates. Again, we're not calling new here. We're calling new inside the calendar, and then we're going to print it out and then exit. Let's see. I don't delete those. Regardless, I added a bunch of dates and events to my calendar and printed them out, and then I exited. Of course, when I run this with Valgrind, I have memory leaks because I never called delete anywhere. I guess I did not save that correctly. Okay, so the solution to that is, well, there's a couple of things. If I remove a date with an event, whoops. Okay, so this basically does again, it's giving me some weird stuff. So I want the equals function. So when I find the first date that has this event, I delete it, I close the gap, I decrement the number of dates, and then I return true. I was successful. If I go through the whole thing and I don't find what I'm looking for, I return false. But the important part here is that I did delete this, right? So I called new inside of this object. So when I remove it, it's my responsibility to call delete. Nobody else knows it exists. And then, any questions on that? All right. And then finally, we simply loop over every element and call delete on it when the destructor is called. So when this calendar is destroyed, every single piece of dynamic memory that was allocated within it is destroyed. And then I have a good object that is responsible for its own memory. And yeah, no memory leaks, right? So in general, that's the strategy I recommend, is using that sort of all the destructors and this domino effect. Basically, in many of your classes, you will have something that looks like this. And maybe you delete a couple other things too. Yeah, questions? Okay, so yeah, memory management does count on assignment 2, which incidentally, I should be releasing this week, I think. It's done, I just have to adapt it to the tutorials and then write the specification, but I don't think that'll take too long. So by the time you're done assignment 1, you should be able to start on assignment 2 if you're really gung-ho. Yeah. It's bonus. If you have no memory leaks, you get I think 2 bonus marks, something like that. Yeah. So if you do all this, you can do all this on assignment 1, and if you do, you get 2 bonus marks. And it is exactly the same strategy, right? But you're just going to do it in multiple classes. Yeah. You can get more than 100%, yeah, but it only counts towards your assignment and tutorial portion, right? So it'll bump up another assignment perhaps, but it won't affect your test marks. Other questions? Okay. How are you guys finding assignment 1, by the way? Didn't start it. All right. You should get a start on it. So anybody else have an opinion? Anybody start it? Yeah. How far? Anybody done? So there's lots of bugs at the end, eh? Is that sort of yeah. So don't wait too long, because you'll get 90% there, and then you'll have a bunch of bugs to track down that are sort of time consuming and difficult. Yeah. It's sort of a couple of loose tests on date. What is it? Trying to remember now. Date, events, and planner dates. Those three things. But then you have to integrate that into the planner, which, yeah. So if your tutorial 3 passes, then you're pretty good, but done it. Oh, awesome. But you'll still have to do the planner class where there's a lot, it's more complex. Yeah. Well, arguably. All right. So I sometimes I'll give you an assignment with a double pointer. Other times, no. They are still in use in C++. I do think they're overrated. I mean, but that's just my opinion, of course. And what do I know? So I can, if I use a getter for a pointer, then that's easy. It works well. It's intuitive. You're not going to make any mistakes. But some people do use double pointers. So what is a double pointer? That is when I pass in a pointer by reference. So we've talked about passing objects in by reference, which means that I pass in the address of that object, and then I can make changes to that object or int or whatever. And then that's a return parameter, right? I can return that value and then use it outside of that function. So when I pass in a pointer by reference, what I want is I want to change what that pointer is pointing to, right? So this is how in, say, this calendar class, if I want to return a date, right? These are dynamically allocated. They live on the heap. So I want to return a pointer to that date. So I can do it using a return value, and that's easy. But I'll also show you how to do it using a double pointer. So we'll go through the example first, and then we'll look at this thing. These were once, double pointers were once all the rage. I don't know if they're super popular anymore, but for arrays? Say you have an array. Right.
So when we did an array of structs, and see if or one is double pointers, like you have the pointer to that array.
Yeah.
That array is always the pointer.
Oh, that's a different application though. Yeah, you're right. Those are double pointers. But that's not, so we're passing, we're returning a pointer. That's what we're doing. But yeah, you're right. You're absolutely right. Those are double pointers. So I think we'll get to that today. I'm just going to move along here a little bit. So in the last, this is basically the same class we just looked at, slightly different though. So before the getter returned a date pointer, but now I'm going to use an output parameter instead. And I'm going to pass in this date by reference, which means I have a pointer to a pointer or a double pointer. Sorry, yeah, up here. Okay. So I'm going to add in some dates, print them out, and then I'm going to ignore this for now. I'm going to make a date pointer and get that. Possible I have to write this. Okay, let's see if this will, let's go Copilot. Okay, good. All right, so let's talk about what it did here. I basically looped through my array until I found an event that equaled my date. And when I did, well, this is sort of the important part. So I passed in a double pointer. All right, let's start from the beginning here. So I'm going to declare a double pointer, and then I'm going to call cal.getDate. What is it? Y2K. And then, well, this takes a double pointer as a, all right, so let's turn this off. So this takes a double pointer as an argument. So the sort of your instincts might be, well, I'm going to make a pointer and I'm going to pass it in. oh, this doesn't work. So then you think, well, it takes a double pointer, so I'm going to make a double pointer. That's also a mistake, which we'll hopefully get to. What you want to do is you want to make a pointer, and then you're going to pass in that pointer's address. Okay, so this gives me a double pointer, right? The address of a pointer is a double pointer. So this is the correct way to do it. There's all kinds of ways you can do it that the compiler will say, okay, all of your types are okay, but you're going to get a seg fault at some point, right? So there is a very specific way to do it. Declare a pointer, and I pass in the address. And then in my calendar class, well, I've passed in this pointer by reference, so I have to dereference it here. When I dereference this double pointer, it gives me back the original pointer that I declared in my main function. And then I assign that pointer to be this date. Okay. And then this is actually, this double pointer here is actually this, what I get back when I dereference date. And then I assign it that value, and then it's reflected outside of that function. Okay. There's all kinds of ways to get this wrong. But yeah, questions? Because they still use them.
String is just, if you have that string dynamically allocated to memory, then you do have pointers to characters, just a list of pointers to characters, and if you pass that list by a double pointer.
Yeah, there's all kinds of stuff. So we're gonna hopefully get to that today. We may not quite get to it, but yeah, there's all kinds of weirdness there. And I'm gonna touch on it. You don't have to, again, you don't have to know all of it as long as you can do some good pattern matching and know what to, what pattern to use where. Eventually, this stuff will sink in, but yeah. So yeah, why do we need it? Because it still gets used, especially legacy code and things like that. I would not write this, but that's, there's better programmers than me that do this. So you can also do, I can pass it by reference. This actually makes more sense. So I'm going to pass a pointer by reference. What does that do? Well, now I can just treat this like a pointer, right? So I just assign it this value, and then when I want to pass it, instead of passing in the address, I just pass the pointer itself. So passing by reference really makes a lot of sense. Passing a pointer by reference. It's not always, I guess, possible because references have some drawbacks that pointers do not. But syntactically, if you want to see what you have to do for a double pointer, think about what you would do if you pass that pointer by reference, and then dereference and address of, add those things to it to get back to double pointers. Okay. Pointers, yeah, so let's quickly go through this. So let's say I declare an int I equals 42. The name is I, the type is int, the value in here is 42. Its memory location is A8. I make a single pointer, I pointer. I'm just going to call it IP, and I'm going to assign it the address of I, right? So that's, so the name is IP. I just erase that. It is type int pointer. Its value is the address of I, which is A8. And its memory location is AC. And then I make a double pointer. All right, so int double pointer equals the address of IP. The name is double pointer. The type is double pointer. The value is the address of IP, which was AC, and its location is B3. So now if I do something like dereference, double pointer, well, it's going to return, well, the first thing it does, the first reference is it says, take this value, go to that location and return that value. So it does, and it returns a memory address. Then this second dereference says, well, follow this memory address and return whatever you find there, which is over here at 42. So if I dereference this twice, I get 42 back. And so that's how double pointers work. Questions? Okay. And yeah, this slide is important. If I do ask you to do double pointers on one of your assignments, this is the correct syntax. Anything else is going to get you a seg fault. I might explain it next class, but we're following a little behind the other class here. So, and there's a better example, which I'm not going to do. So yeah, we'll quickly talk about arrays, and then that should take us to the end of class. So we've talked about statically allocated arrays, right? So what those are, and we talked about two types. So I have my function main, let's say, or statically allocated or whatever. I can have a statically allocated array. Actually, let's look at the code first, and then we'll look at the model. So I have the date class, which is what we're going to be storing in our arrays. We have a default constructor. So if I make an array of objects, this will be valid. And then I have, so I define max size to be 2 here. So we're going to make arrays of size 2, but they still work the same. I've got 4 functions. And what those 4 functions are is the following. So we're going to introduce, so we've seen static arrays, and we've seen static arrays to pointers, and we've seen static arrays to objects, right? So now we're going to introduce a second type of array. It's a dynamic array, but dynamically allocated arrays can also be arrays of objects or of objects pointers. Okay, so before we always had our arrays statically allocated, maybe in a class or in a function. But that's not really a great idea, right? So it's fine for these arrays of size 2 and 3 or even 100, but a size million on our stack is going to take up a lot of memory that should go on the heap, right? So dynamically allocated arrays are generally speaking preferred because they end up on the heap instead of the stack. And they save us that stack space, which is a valuable resource. Declaring a dynamically allocated array, I use the new with the square braces, right? And of course, the square braces will contain a number. That number will be the size. And I'll also have a type as well. But in general, when you see new square braces, I'm declaring an array, dynamically allocated array. And when I delete a dynamically allocated array, I have to use this special delete syntax. In this case, there will be no numbers in these square braces. You will write exactly this. But this tells the compiler that I'm not just deleting a single object, I'm deleting an array. All right. So yeah, we have 4 types of arrays to look at. We have statically allocated arrays of objects. We have dynamically allocated arrays of objects, and we have statically allocated arrays of pointers and dynamically allocated arrays of pointers. Each is slightly different, although they have a lot of similarities as well. Let's start with the simple one, statically allocated objects. So all I do is, well, it's of type date. These square brackets mean it's an array of size 2. And if I look at my memory map, then what happens is this is my statically allocated function, and I made 2 dates in the stack frame on the stack in an array. And then I can print them both out using this a subscript, which tells the, tells the operating system to go to that location in the array and then find the object there and print it. So we can, okay, so printing the array, of course, it was an array of objects. So the default constructor was called for both of them. So both are January 1st, 1901. And then it's automatically destroyed for me. So I didn't destroy anything. Yeah, statically allocated array of objects. We've seen that before. One interesting little aside, and again, if you find this confusing, just forget it. We will rarely use it. This is the important part, what you see here, but this ARR1 is actually a pointer to a date, right? So if I want to have a second reference to some array, I have to declare a pointer, right? So arrays, the variables that point to arrays are actually pointers in disguise kind of thing. Not in disguise. It's really interchangeable. So I can declare this and I can assign it a new date, or I can assign it this array of date objects. And then I can use this ARR2 the same way that I did ARR1. Right? So yeah, it's a pointer, but it's pointing to an array, so I can do subscript operator on it. And if I wanted to, I can assign it to a date object or a date, a dynamically allocated date, and use it that way as well. So yeah, array variables are pointers behind the scenes. Questions? Yeah. Declare strings. So they're wrapping it in an object, basically. So a string is an object in C++. So it's not really a primitive. We treat it like, yeah, we treat it like one, and we'll talk about that actually a little bit later too, when we get to encapsulation and consting things. But yeah, it really is. You can use character arrays the same as you use in C, but we tend to use strings. They're way easier. Yeah, that's exactly it. Yeah. Other questions? Okay. So 5 minutes, 7 minutes. All right, so let's go through these quickly. So statically allocated array of pointers. Well, this is exactly what I asked you to do on the assignment, right? So statically allocated array of pointers looks like this. I declare it's a statically allocated array because those two square brackets are there. There's no new, but it's of type date pointer, right? So then I can do things like make a new date pointer and assign it to the first location, or I can simply allocate a new memory location and assign it to the second location and then print those things out. Is it though? So I don't think it is. Okay. And so, yeah, we get May 5th, 1955 and June 6th, 1966, which is the dates that we put in. Of course, we have to explicitly delete them in order to not introduce memory leaks. Okay. Quick questions on that? All right, let's get through this and then I'll take questions at the end, I guess. A dynamically allocated array of objects. So now the array goes on the heap along with some objects. So I'm going to have a double pointer here, and this is my heap. I'm going to dynamically allocate this array, and inside it will be 2 date objects. Okay, and then syntactically, this is the same as a statically allocated array of objects. The only difference is it exists on the heap, but as far as this pointer is concerned, it has no idea. It doesn't care where it is. It's just a memory location. So yeah, dynamic objects. in a rush and I'm just missing it. Oh yeah, cool. It's right here. So yeah, to do this, I have the new and I have the open and closed square brace, right? So that means this is a dynamic basically because of the new, it's a new array that's going on the heap, and it's of size max size, and its type is of date. Okay, and here I explicitly assign it to a pointer and a date pointer. And then I can take that date pointer, I can use the subscript operator, and that returns an object, and I can call print on those objects. And if I want another handle to that same array, I declare a second pointer. So yeah, let's take a look at that. Yeah, so these are date objects. So I called the default constructor, and I got January 1st, 1901. When I delete it, I use this special delete syntax. And I got to tell you, you'll probably see me do it. I always forget to put that in. But that's going to give you, hopefully it'll give you a seg fault. Occasionally it actually works. Or it works, but you get a memory leak. So yeah. Questions? All right. So the last one is the dynamically allocated array of pointers. And this is probably what we would recommend. This is definitely what you're supposed to do on assignment 2. So you're going to make here, this is my new array. So that means this is going on the heap, and the type is of date pointer, the size is of max size. And here I explicitly have to declare it as a double pointer. Okay, and because that's basically what it is. So in terms of my memory diagram now, my array is on the heap, but inside it is date pointers. When I assign new dates to them, I make new date objects on the heap, and then these are pointing to those date objects. So now everything's on the heap, and I only allocate as much space as I need, really, for date objects, although my array might be big. So yeah, I can do things like make a date pointer and assign it to the first location, make a new date, assign it to the second location, and then I can, what is wrong with you? Very slow. Right? They both print out. The last thing before we go, so you have to delete this array, but you also have to delete the 2 locations, right? So array 40, because that has a date, dynamically allocated date object that it's pointing to, and so does that. So to delete it completely, I have to delete everything in each of the locations and then delete the array itself. Okay, and then that's fine, and that's the order you want to do it, right? If I look at my thing, first I'm going to follow my pointers and delete this guy, and then I follow my pointers again and I delete this guy, and then I delete that. If I do it in the other order, again, so I have these pointing to dates. Let's say I delete my array first, and then I try to follow these pointers and delete these. Mostly I'll get a seg fault. Occasionally it'll still work. So yeah, but yeah. So in this case, order is important. Do this. Don't do that, right? That could be disastrous. It's even worse if it doesn't crash right away and crashes later, but yeah. So questions on that? Okay, so that's it for tonight. So this will actually be on tutorial 4. All of these different types of arrays and how to access data from them. But yeah, I'll see you guys on Wednesday.